Welcome to this lecture. In this lecture, the two fundamental concepts in astrophysics and statistical mechanics will be explained. These two concepts are collisionless Boltzmann equation and Jeans theorem. Jeans equation comes out from the theoretical calculation of collisionless Boltzmann equation and the application of Jeans theorem. In this lecture, the physical significance of some of the terms of the collisionless Boltzmann equation will be described, along with why these terms or functions are used in the equation. The collisionless Boltzmann equation has some limitations. I will explain the conditions under which it holds true and its limitations in accurately describing systems with non-negligible collisional interactions. Jeans theorem is needed to solve or find the solution of the collisionless Boltzmann equation as it relates the statistical properties of a system to its gravitational potential. In addition to that, I will explain the mathematical derivation of the Jeans equation, how the Jeans equation connects the distribution of particles in phase space to the gravitational potential of a system, and why we need the Jeans equation. Let's delve into the cornerstone of collisionless systems, the collisionless Boltzmann equation. This equation encapsulates the dynamics of systems where particles interact predominantly through gravitational forces rather than collisions. It plays a crucial role in describing the evolution of distribution functions in phase space, offering valuable insights into the dynamics of systems such as stellar clusters, galaxies, and dark matter halos. The equation as presented in the slide takes the form full time derivative of f is equal to partial time derivative of f plus v vector dot gradient of f minus gradient of phi dot del del v vector of f equal to 0. Here, f represents the distribution function, or also known as phase space density, which is a function of position vector x, velocity vector v, and time t. Here, phi denotes the gravitational potential. What makes this equation fascinating is its collisionless nature. During two-body relaxation phenomenon, stars exchange energy and angular momentum. It requires time to do this process, which is known as relaxation time, that we have denoted as T relax. But for many stars, T relax is immense. For instance, consider our Sun, which has a relaxation time of approximately 10 to the 13 years. The term collisionless signifies that the system's typical relaxation time is much longer than the timescale of interest. That is why this equation is known as collisionless. Now, why we need distribution function to describe this system? We could have tracked a single star and put it into the equation and find the statistical properties. Imagine dealing with a system comprising billions upon billions of stars. each with its position and velocity. The sheer scale of data storage required is mind-boggling. As noted on this slide, if we attempted to store the position and velocity of each star, it would demand an astronomical amount of memory. For example, for 10 to the 12 stars, if we try to store the position and velocity of a star on a computer as 4-byte numbers for every star, it would take 6 into 4 into 10 to the 12 bytes, which is equal to 2 into 10 to the 13 bytes. The storage requirement would be prohibitively massive. Even with modern computational capabilities, storing such vast amounts of data for each time step, like 10 to the power 3 to 10 to the power 6 steps, would be impractical. This is where the distribution function comes to our rescue. By representing the system in terms of the distribution function, we can numerically store it with modest data resources, making it computationally feasible. Also, this function lends itself to analytical modeling, allowing for deeper insights into the behavior of collisionless system. Now, let's explore a critical aspect often overlooked in the application of the collisionless Boltzmann equation, the finite lifetimes of stars. In the traditional formulation of the Boltzmann equation, it assumes that stars are conserved, hence resulting in a zero term on the right-hand side of the equation. However, in reality, stars are born and eventually die, rendering this assumption inaccurate. To rectify this, we need to modify the collisionless Boltzmann equation. The correct form accounts for both the birth and the death rates of stars per unit phase space volume. The modified equation takes the form as it is written in here. The left side did not change from the original equation, but in the right side we have b minus d. Here b and d both are function of position vector, velocity vector, and time represents the rates at which stars are born and die, respectively. Now let's delve deeper into the implication of the finite lifetimes on the collisionless Boltzmann equation. The second term on the left side can be rewritten as this equation, like v vector dot del del x sub f. If we express the velocity and the position vector here as a characteristic speed and characteristic radius in the galaxy, then we can write v multiplied by f by r. So if we do a little bit of rearranging, we get f by r by v. Here r by v is known as t cross or crossing time. The crossing time is the time needed for a typical star to cross the galaxy once. Now this ratio, the ratio of the second term to the right hand side, can be denoted as gamma, is equal to B minus D by F by T cross. Now, if gamma is much less than 1, then the collisionless Boltzmann equation remains valid. For some stars, gamma is much less than 1, and for some stars it is not. For instance, in the case of M dwarfs, which have a very long lifetime, the distribution function remains relatively stable. However, for stars with shorter lifetimes, such as O stars, the assumption of stellar conservation breaks down. That means in this case, the right side is not zero anymore. And the collisionless Boltzmann equation cannot be accurately applied. Let's now talk about another crucial limitation of the collisionless Boltzmann equation, the presence of correlations between stars within a system. In the collisionless Boltzmann equation, we often make an assumption about the average number of stars within an infinitesimal volume of phase space denoted as NF. However, in practical observation, we have experimental limits, and we cannot take a measurement in infinitesimal volume. Instead, we measure the number density in finite volumes of phase space, leading us to consider the average distribution function denoted as F bar within that volume. Now, this assumption holds true only if the stars within the systems are uncorrelated or separable in phase space. Mathematically, if we consider two stars, star 1 at position U and star 2 is in position U prime, then the probability of finding star 1 in position U will be integration of F U D to the 6 U. And finding the position of star 2 will be Fu prime D6 U prime in this case. But if we want to find the probability of the stars, both of these stars in these positions, it is given by this equation as it is written in the slide. P of S is equal to integration of F of U prime d to the 6U d to the 6U prime. So it is only possible if the stars are uncorrelated. However, this assumption of separability breaks down in real systems. In a correlated system, the presence of one star at a certain position increases the likelihood of finding another star at a different position. Consequently, the probability distribution of stars within the system is not separable but correlated. This correlation between stars introduces complexities that cannot be captured by the traditional collisionless Boltzmann equation. The assumption of uncorrelated stars leads to inaccuracies in modeling the dynamics of systems, particularly in dense environments such as star clusters and galaxies. Thus, it's essential to recognize and account for these correlations when applying the collisionless Boltzmann equation to real astrophysical systems. For solving the collisionless Boltzmann equation, we need Jeans theorem. Jeans theorem lies at the intersection of dynamics and statistical mechanics. At its core, Jeans theorem revolves around the concept of integral of motion, an essential property in celestial mechanics. An integral of motion, denoted as I, x vector, v vector, where x represents position vector and v represents velocity vector, is any function of the phase space coordinates alone that remains constant along an orbit. In simpler terms, it doesn't change as a celestial object moves through space. Mathematically, we express this property as for time t1, we have integral of motion ix t1 v t1, and for time t2, we have another integral of motion ix t2 v2, and both of them are equal. This implies that the time derivative of integral of motion will be 0 along the orbit. By taking the time derivative, as you can see, we can reach into the equation v dot del del xi plus a dot del del v of I equal to 0. Here, a represents the acceleration of the object, which depends solely on its position rather than time, as it is governed by the gravitational potential phi. As we can see, the acceleration is equal to F by m equal minus gradient of gravitational potential, or phi, which can be expressed as minus del del x of F. Therefore, we obtain, if we use these equation instead of A, we get this equation, v dot del del x of I minus del phi by del x dot del I by del v is equal to 0. Now, here's where it gets interesting. If we compare this equation with the collisionless Boltzmann equation, we notice something intriguing. The condition for I to be an integral is identical to the condition for I to be a steady-state solution of the collisionless Boltzmann equation. Based on this realization, English scientist Jeans formulated a theorem aptly named Jeans theorem. Jeans theorem is a pivotal result in statistical mechanics, establishing a crucial link between the integrals of motion in celestial mechanics and the steady-state solution of the collisionless Boltzmann equation. Jeans theorem is a fundamental result that underscores the importance of integrals of motion in solving the collisionless Boltzmann equation for gravitational potentials that remain constant over time. Essentially, Jeans theorem states that any steady-state solution of the collisionless Boltzmann equation is solely determined by integrals of motion within the given potential. Moreover, it asserts that any function of these integrals yields a steady-state solution of the collisionless Boltzmann equation. In practical terms, this means that we can express the collisionless Boltzmann equation in terms of integrals of motion within a time-invariant potential. We can then solve for the distribution function f in terms of these integrals of motion, subsequently by converting f in terms of integrals of motion to a solution in terms of space and velocity coordinates, we can gain insights into the dynamics of the system. However, it's important to note that while this proposition offers a promising approach, its utility is somewhat limited. One of the primary challenges lies in the fact that the often respected integrals of motion lack analytic expressions. This limitation poses significant hurdles in practical applications, especially when dealing with complex systems. For example, consider the scenario depicted in Figure 1a, where stars are following an orbit. Now, if the total angular momentum of the orbit were conserved, the trajectory of the stars would align with the dashed curve shown in Figure 1b. This curve represents the path traced by the stars over time, maintaining a constant angular momentum. However, it's essential to note that full curve depicted in Figure 1b, the zero velocity curve at the energy level of these particular orbit. This curve delineates the boundary where the kinetic energy of the stars equals their gravitational potential energy, resulting in zero net velocity. Now observe the marked X symbols in Figure 1b. These marks represent the consequence of the shell orbit, the specific locations where stars are positioned along the orbit. Each cross corresponds to a point in phase space, capturing the position and velocity of a star within the system. In this example, the integral of motion for these curves does not have any analytical expression. So this theorem, or the theorem proposed by Jeans as his first proposition, is not as helpful as we wanted. According to the first proposition of Jeans' theorem, we understand that the distribution function is a function of integrals of motion whose specific form remains unknown. This forms the foundational premise upon which Jeans' theorem is built. Moving forward, we encounter a crucial observation. If every orbit in a galaxy is regular, we can disregard any non-isolating integrals. This insight is substantiated by the time average theorem, which underscores the regularity of orbits within the galaxy. This leads us to another proposition arising from Jeans' theorem, the strong Jeans theorem. This theorem states that the distribution function of a steady-state stellar system where almost all orbits are regular with non-resonant frequencies can be presumed to be a function only of three independent isolating integrals. These integrals, known as actions, encapsulate the essential dynamics of the system. Therefore, according to the strong Jeans theorem, a steady-state galaxy can effectively be represented by a distribution function of the form f I1, I2, I3, where I1, I2, I3 are three independent isolating integrals. This simplification arises from the regularity of orbits within the galaxy driven by its gravitational potential. Now, the choice of distribution function and the relationship between moments depends on the system of the galaxy or the stellar system. For example, a system which has an equilibrium stellar system, in this case, distribution function is any non-negative function of h. That means df depends only on Hamiltonian h. As it has the velocity dispersion tensor that is same in everywhere. That's why it is known as isotropic system. In case of statistics, it is known as ergodic system. In a spherically symmetric system, the distribution function depends on both the Hamiltonian and the angular momentum. And in an axisymmetric system, the distribution function depends on the Hamiltonian and the angular momentum Lg, angular momentum component Lg. These distinctions highlight the tailored nature of distribution functions in capturing the unique dynamics of different stellar systems. For proving Jean's equations, we need to establish the connection between the distribution function and observables by defining several key quantities. Probability per unit volume of finding a particular star at position x defined by its velocity, denoted as Vx, is equal to integration of dqb f of x vector v vector. The number density of stars defined as the product of number of stars and the probability per unit volume. The probability distribution of stellar velocities at position x, denoted as pxv, is calculated as the ratio of the distribution function to the probability per unit volume. The mean velocity at position x, represented by v bar x, is obtained by integrating the product of velocity and the probability distribution over all velocities. We can also express it in terms of distribution function using the definition of the probability distribution. The velocity dispersion tensor, denoted as sigma square ij, describes the dispersion of velocities around the mean velocity at position x. It is computed as the second moment of the velocity distribution. Velocity moments of the distribution function, such as the mean velocity and the second moment, often serve as focal points for comparing theoretical predictions with observed data. These moments provide valuable insights into the dynamics of stellar systems and are instrumental in evaluating the consistency between theoretical models and empirical observations. Calculating these velocity moments is a straightforward task, as they involve simple integrals over the distribution function. However, the challenge arises when attempting to find a distribution function that is compatible with a particular probability density distribution inferred from observational data. Despite the seemingly straightforward nature of this task, identifying a distribution function that matches observational evidence is often a non-trivial endeavor. Furthermore, even when a candidate distribution function is identified, it may not be unique, leading to uncertainties in the interpretation of observational data. So, the Jeans equation, a powerful method that circumvents the need to directly retrieve the distribution function by leveraging stellar densities to deduce velocity moments. The Jeans equation provides a practical approach for inferring velocity moments from observed stellar densities, offering a valuable tool for proving the dynamics of stellar systems without requiring detailed knowledge of the distribution function. By integrating the collisionless Boltzmann equation, as discussed in the previous slide, over all velocities, we arrive at an expression as written in the slide. Now, it's crucial to note that for sufficiently large velocities, the distribution function tends towards zero. Consequently, the third term in the left-hand side of the equation becomes negligible, simplifying the expression to this line. In this case, velocity is a function of velocity vector, not a function of position vector or time. That's why we can take those derivatives outside of the integral, and then we can use the definition of probability per unit volume and the mean velocity, which simplifies this equation to del v by del t plus del v vi bar by del xi equal to 0. This equation is the first Jeans equation, a fundamental tool in understanding the dynamics of collisionless systems. The first Jeans equation differs from the traditional continuity equation in two key aspects. One, it describes the conservation of probability instead of mass, reflecting the unique nature of collisionless systems. Two, it substitutes the mean star velocity for the fluid velocity, highlighting the statistical properties of stellar distributions within these systems. For finding the second Jeans equation, we need to do a little bit more algebra. If we multiply the collisionless Boltzmann equation, as in the previous slide, by Vj, and integrate over all velocities, we can write the equation as in the first line in this slide. As in the previous slide, the velocity is a function of velocity vector, not the function of position and time in the phase space. We can take out the derivatives from the integral, which has been done in this second line or equation 1. In case of third term, we can apply integration by parts for the integral part of it, and we can use the concept that for sufficiently large velocities, the distribution function tends towards 0, which leads us to delta ij v for the integral part of the third term. Substituting equation 2 into equation 1 and utilizing the relationship between the distribution function and observables, we derive equation 3. Next, by multiplying the first Jeans equation by Vj and subtracting it from equation 3, we arrive at this line into the slide. After doing a little algebra, we will get equation 4. This equation, known as the second Jeans equation bear similarities to Euler's fluid flow equation. However, there are notable distinctions. Instead of mass density, it uses probability density, reflecting the unique nature of collisionless systems. The mean star velocity, VI bar, is employed instead of fluid velocity, underscoring the statistical properties of stellar distributions within these systems. The last term on the right side of equation 4 represents the pressure force, or more precisely, anisotropic pressure akin to the pressure gradient term in fluid dynamics. As we can see, Jeans equations are a mathematical expression with probability density, mean star velocity, and pressure force. However, it does not have a distribution function in the expression, which allows one to avoid the distribution function for stellar systems. Thank you for listening to this lecture. If you have any questions, please let me know.